There's homework. Write a Python program using PyElf tools and Capstone, which we've talked about, and there are examples of using those in the previous lecture, that takes a single argument which specifies an executable file. Open the file, locate the .text section, and disassemble all the code in that section. Now you saw me do that last time, but I sort of did it in an ad hoc way. Name your file disassemble.py, and this is what the output should look like. So you should have, in this case I gave it ls, and here's what you ought to get for the output of ls. It ought to start at 4DA0 with the call, and it ought to end at 175.6D with the jump. Print the address in front. Look at there. There's a nicely formatted 16-character hexadecimal address with the leading 0x. And then print the opcode and the op string out here at the end. Check your arguments. So watch for things like file not found error. Maybe it's a directory or there's a permission error, whatever. I don't expect you to do a huge amount of checking, but I expect you to catch obvious cases, like be running your thing without a file or running it with a file that's not an ELF file. Catch those and let me know. Well, what if it's not an ELF file? How will I know? Well, ELF file will throw an error, and it will throw this error right here, ELF error. Great. Also, you might watch for either one of these things, either open or the constructor for ELF error returning none. Might be a possibility, something you can watch for. You can check that by asking whether the variable that's returned is none. Okay. For debugging and errors, don't print a bunch of stuff because that will confuse the automated checker. Instead, I've made available to you a little package called debug.py. It's a little Python module that defines some stuff. In particular, it defines a function called debug. And so you see that's how you use it. You just say debug in main, and that will print a debugging message. They look like what you see down here. And if you don't enable debugging, they don't print. It's very, very lightweight. Error, if you want to print an error, that prints it with this nicely formatted error colon in front that the automated checker can pick up and extract. And you can even do some neat stuff, like you can pass options in the debug variable, which is parsed at the prompt from whatever's in the debug's environment variable. So like here, I've set it equal to debug, so I've turned on debugging. That's how you turn it on. But I've also added Fred. What the heck is Fred? Well, I can check for Fred at runtime in my program this way, and then I can print something out if I want to do it, or I can make different choices, whatever. There you go. Please use this. It's just much simpler. It's available on the iLearn site for this assignment. Some hints. Try to work through this at the IPython prompt. I think that will save you a lot of trouble if you just sit there at the IPython prompt and you work your way through doing this for some executable. It's going to make you a lot happier. Handle the error cases. Format your address this way, so that, again, it's not a whole lot of different crazy things coming at the automated checker. Nice leading zeros, 16-character hexadecimal number beginning with a 0x. So simple, just use that. There we go. You might need some imports, and so up here is typically how you would start your Python file. Be sure and have documentation strings in it. Import sys. You'll need that to get to the arguments. They're in sys.argv. Import elf file. You'll need that to parse a stream as an elf file. Import elf error. That's what you'll get when you can't parse a stream as an elf file. From Capstone, you'll need CS, because that's how you make disassemblers. You'll need Arch x86 and Mode 64, because Capstone supports 32-bit code, and it supports ARM code, and a bunch of other stuff as well, and you have to tell Capstone this is what we're going to be using. You can get creative, and you can look at what platform you're on and use that by default, but don't bother with that. Just use those. From the debug module, you can use debug and error, and if you want to use the all caps debug variable, just import it too. Use pylint. It will really help you, okay? It will really help you. And you may need other imports than you see here. Those are the ones I think will get you started. So let's talk tools. Tool today could be GDB or it could be Python. It's going to be a combination of those. One of the things that I like about GDB, modern GDB, that sort of brought it back into favor with me, is that it's pretty easy to extend it with Python. And that's another good reason to learn Python. Python is a language that is directly supported in GDB, meaning if you're running GDB, it's got Python baked into it that you can use. And using it is pretty simple. So let's go ahead and start up GDB. If I want to do something with Python, I start a line with py, and then I can have a Python instruction. And one of the nice things about this is it's persistent. So here if I define x to be 5, later on I can print x and I'll get 5. And the same thing is true for doing stuff like importing packages. So now I can print something out. In particular, let's print version, which is the version of Python we're running. We're running 397. So that's pretty handy. And I can't just say py(x) because it doesn't print that out. I have to print out the result. What if I want to do something longer than that? Let's say I want to do a loop. So let's say for x in range 1, 4. Oh, doesn't work because I can't type multiple lines. To do something like that, I would just say py on a line by itself, and I'm ready to start entering information. So now I can do a number of things. I could say for x in range 1, 4 colon print x, and just typing enter on a blank line doesn't work, doesn't end the block. I have to explicitly end it with an end, and there you go. So that's how you can do stuff with Python directly in here. If you have a file that has some Python commands in it, you can source that file, and that will work just fine. And you can put these kinds of things, sources and so on, in your .gdb init. So here's a longer example of defining a function, in this case, at the GDB prompt. Bytes displays the bytes at the current program counters. These are the bytes located where RIP is, the 16 bytes of RIP. And the way it works is we go and use GDB. That's a package that provides the Python interface to GDB. And we go get the inferiors. Now, inferiors are basically files that have been loaded by GDB. So we get that, and that's the file we're debugging. Frame gets the selected stack frame, right? Could be multi-threaded. There could be many different stack frames. Each one of those has its own program counter. We want the program counter for the frame that's selected right now. And by getting frame, we're then able to do this to get the program counter for that particular frame. So this is going to give us the value of RIP. Then we go to the inferior, read memory, starting at RIP, going 16 bytes, and that returns a GDB memory struct to us. We convert it to a byte array with 2 bytes, and then we iterate over that. We print out each byte. We don't have a new line at the end. This lets us suppress the new line. And then we print a new line after we printed the whole thing, and we have an end, and we're done. Then we can just call it like this. So this is just defined it at the prompt. That's a lot of stuff going on in here, but this is all well documented here in the Python documentation that's part of the GDB documentation. And in addition, it's worth pointing out you can do this. You can get help at the GDB prompt for Python, just like you could at the Python prompt. And so you can see here's the GDB package that contains a whole bunch of stuff. And this tells you what all that stuff is. And you can walk through here and take a look. And there are some examples created online. Quitting the pager confuses GDB a bit because it terminates the Python process and you get a Python exception. But it's fine. No harm, no foul. So what might a larger Python extension look like? Well, I actually have one of those. Let's get a bigger window. And I've got this Python file sitting here. And it looks like any other Python file that you might create, with the exception that it's got this import GDB. Now, GDB is a runtime package that's always available to your Python code, so that import is really unnecessary. It's just there for reference. And Pylint's going to complain about it because it can't find GDB, right? Because GDB is, again, sort of inherent to the GDB code. So I have a little comment there to suppress the Pylint warning about it. I create a new command, continue until op. It extends this class, GDB command, which is the base class for all commands. And the doc string you see here will become the command line help inside GDB. So the init method initializes the object, but it also sets it as a command. This is how you specify that it's a command. You call the superclass constructor and pass the information along up to GDB. And I want to be able to use capstone in addition to using GDB's own internal disassembler. So I actually have a switch -C or -G to specify which one to use. And then I go through the work of doing what you would normally do, right? You see down here, I'm printing out the address and mnemonic and op string, and this is if I'm using capstone. Up here I do much the same thing, but do it for the GDB interface. The very last line, I make an instance. That's going to cause init to run, which is going to install this as a new command inside GDB. Does it all work? Well, there's the command line help. That's a good sign. Let's go get a file to take a look at. Pick on our old friend ls. Let's start it. That's important because addresses get fixed. So now if I say info file, there we go. I can see what the correct entry point is, and I can set a breakpoint there. And great. Now, I wanted 20i. There we go. This looks like what I saw in CRT 1.0. So let's go ahead and run until we get to this call right here. So let's do CI call. And you see it prints out the addresses as it goes along. And then we stop here at this call. And if I do a listing again, you see we're right here. We haven't executed the call yet. We're just about to. Now we know the first argument to that is going to be in RDI, right? So we can print out what's in RDI, and this should be the location of main. So we'll continue, and we hit breakpoint 2. Use a little trick, and there we are, ready to start debugging at main. So the little continue until is fairly handy. So for example, this main has a lot of pushes, move, push, sub, move, XOR, and then there's this call. So let's go ahead and CI call again. And you see now we've jumped down to where that call is, and we can see what's going on there. So moderately useful little command. And you can extend it in a variety of ways. And in fact, you can imagine somebody could make a whole bunch of different extensions to GDB using Python and really enhance it. And that would be great. You can put your general extensions I like to put them in a .gdb folder, and then I just source them out of my GDB init. So in my GDB init, I just a source that points to a .py file, and I'm good. I can, of course, have py commands in there, but I can't have the longer multi-line ones. There's no way to put those in your GDB init that I know of. And so there you go. Someone could build a whole lot of cool extensions to GDB, and someone has. And that set of extensions is called GEF. You can read about GEF right there. You can install it pretty easily. There's a one-liner. If you don't like running scripts that someone just provided off the internet, you can go ahead and get the script using wget, and you can read through it yourself, just a bash script, and then if you're comfortable with it, you can run it. Basically, all it's going to do is clone a repo locally and add a line, or I should say, replace your GDB init with one that sources the resulting Python file. And if you want to uninstall it, you just remove that source line and you can delete the file. Easy stuff. If you have a GDB init around and you run this and it does damage to it, it saved your GDB as gdbinit.old. So just do it once, make sure everything's right, and if you need to restore it, you can restore it from here. If you do it twice, it's going to overwrite this and you'll lose some stuff. All right. What does GEF do? Well, it gives you a lot more information when you're debugging. That's one of the cool things about it. Instead of having to work with that little TUI interface, you can use GEF's interface, and it works by just printing out a whole bunch of extra stuff each time you execute an instruction in the thing you're debugging. And so you see up here, it's printing out the registers. And it tries to give useful information about some of those, like RSP is the stack pointer. It's pointing here. The contents of the stack at that point are 1. That is argc right there. It prints out RIP, and since that's the instruction pointer, here is the instruction it's pointing to. It decodes the flags register for you. There it is. It does E flags. And it prints out the segment registers down here. Doesn't print out the floating point registers and that stuff, but that's okay. The stack tells you the top 8 things on the stack. The very top of the stack is right here. RSP is pointing to 1, which is argc, which we knew from looking up here. The next thing below that is the argv array, which is null terminated. In this case, there's one thing on it, this, which is a pointer to this character array. Right, so it looks like we're debugging. When I took the screenshot, I was debugging Python. That's followed by your environment, and we just see the first few because, again, it's just the top 8 things on the stack. Then it shows you your current disassembly with your current location right here. It tries to do a decent job of winding backward, which is hard for a number of reasons, and showing you previous instructions, and then showing you the ones going forward. It tells you about where you are in the world, and that's it. It gives you this information, and updates the information every time you run an instruction. And unlike the TUI, where these are separate windows that can get focused and scroll around, this is just stuff it prints out. So your up and down arrow still works here, and this is just printed out. It's pretty nice. We can take a look at that. Go pick on ls again. Now what I've done, instead of just straight up sourcing it, is I have a command that I've defined, get GEF, and when I run it, its body of this is just it just sources the GEF Python file, and there you go. I guess I should show you how I did that. It's pretty simple. It's up here at the top. I define get GEF to be sourcing that thing, and there's my end, and then you can document you can create a command this way with just lines of GDB commands, and you can document it this way as well. So there you go. So back into GDB. If you just install GEF, you'll be in GEF by default, but there's lots of times when I want to show you stuff that's in vanilla GDB, so I do it this way. And so let's go ahead and do a start I and watch what happens. Now we get all of this information. And so up here are the registers. Here is my stack. Here's a disassembly with my current position. And remember, this is a stripped executable. Right? I was not getting this information when I was just running GDB normally, but GEF provides it right here. You can see I'm pointing at a move. If I take a step, it updates all of that. So it's sort of hard to see that it's updated, but it shows you registers are updated, and it's scrolled off the top. Modified registers are in bold red. Here, pointing to code, a heap stack. It color codes them here to help you. And you can see now we're pointing to the next instruction, which is this call. And GEF's kind of handy. It says, oh, look, there's a call. Let me show you what's there. So you see the little arrow here, and now it's showing us the instructions at the target of that call. And so if we take another step, there we go. Now we're inside that call and right here. And if you look up here, you can see what's happening up here on the stack. Look at there. There's our return address. Right? That's our return address. And RDI is pointing right here. And RSP is pointing here. So you can sort of see how different stuff is happening as we move through an executable. Right now, we've just been in the dynamic library start, so we would expect the OS to provide us with our argc and argv and all that on the stack. When we get to main, we won't expect that to be the case. So this is very handy for seeing what is where on the stack as we move through a program. In addition, I should mention eFlags up here. So if I say flags, I get that full decoded eFlags down here, and I can actually modify the flags. So for example, I could set, let's say, carry, and now carry is set. And I could clear carry with a minus, and I could, let's say, set parity. And there we go. So stuff like that, pretty easy to do. There's other stuff. In particular, there's information about the heap. It turns out to be pretty helpful to get information about heap chunks. And in this case, they're undefined. Just the executable hasn't run long enough to need to start setting up stuff in the heap. Let's see, what else can we get? We can just get a whole lot of other information about the program. We can get information about the ELF file, which was started, and you can see here the ELF headers. Here are the program headers, or the segments. And here are the section headers. And there's just a lot of information you can get. So, if you happen to have Capstone installed, GEF can use it to do this assembly. If you have Keystone installed, that's a Python library to do assembly, GEF can use that to assemble code at the prompt, which can be kind of handy. If you know what ROP gadgets are and you want to work with them, and you know what Ropper is and how it works, you can work with Ropper directly from inside of GEF. Lots of other stuff in here. In particular, if you just type GEF by itself, it gives you a list of all this stuff, and there's a lot of stuff here. My window's not quite wide enough for it to not wrap. There we go. And so, you can see address-based layout randomization, assemble. You can look at the stack canaries, disassemble using Capstone. Checksec's in here. What else? If I want to print the GOT, there's what's in the GOT right now. Remember, the GOT didn't go away. It's still there, and it's still being used. And this lets me see what's going on inside the GOT. I can search for stuff. I can stub out functions. I can, if I'm about to do a syscall, I can say syscall args, and that will decode it for me and show me what's going on, and that's pretty handy. I can output traces. Lots of fun stuff that you can do. There's a much simpler way to dereference stuff, which is to use dereference, which dereferences recursively This is really, really handy. It turns out this is much better than trying to fool around with X and these other things to figure out what's going on. Registers is, gives you that registers listing that you saw earlier. So lots of good, helpful stuff in GEF. Let's talk about NASM macros, and this applies to NASM. Other macro assemblers have their own macro languages that will be different. So all modern assemblers are what are called macro assemblers, meaning they have a preprocessor like CPP for C, and they preprocess your assembly, and they can expand macros and do substitutions and import files and all the other things that preprocessors typically do. Documentation on the NASM preprocessor, including how to do imports, which you've seen before, conditional assembly, and macros, that's all in Chapter 4 of the NASM documentation that's online. Simple definitions are easy. It's easy to define constants. In NASM, you just use EQU to define a constant. A little more complicated stuff, you can use percent define, which is like pound define. It's very much like pound define. And you can see here I define numerator to be this thing right here, the Q word at RBP minus 8. Denominator is defined to be the Q word at RBP minus 16. And when I see a minus, RBP minus something, I tend to assume local variable, right? Because that RBP points to where the stack was on entry, and then this is pointing at a lower address, and the stack goes downward as you add to it. So this is something that's inside my stack frame, and so therefore it's probably a local variable to me. Or I can define a little more complicated ones. So as you know, in CPP, I can have arguments to my pound defines, and then I can include them over here by name, and you see I've done that right here. And just like with CPP, it's a good idea to enclose them in parentheses so that they don't accidentally glom onto something next to them. And you also have to remember that, like CPP macros, NASM macros are not hygienic. If you don't know what hygienic macros are, don't worry about it. That just means that if I'm using the name index somewhere and I substitute here, I have to be very careful about that I don't accidentally capture a variable when I don't mean to. Okay. Longer ones. Now in CPP, I would use continuation characters and define a multi-line macro that way, but NASM actually has a multi-line macro facility. You start it with % macro, and you end it with %n macro, and then inside here you have the body of the macro. There's some stuff to realize. I don't have symbolic names. I give the name of the macro, and then I say how many arguments it has. In this case, I've got 2. And the 2 arguments are going to be %1 and %2. Well, what is this thing right here, this %00? That's not a %1 or a %2. This is a variable that captures the argument directly in front of the macro invocation. So over here on the left, I say size colon, and then I invoke error, and so 00 would be that label size. It's a way for me to refer to the label inside here. There's the first argument, there's the second argument, and they're just instantiated in place. And so if I had an invocation like this, size colon, error, size exceeded, comma 10, this gets bound to %00. The arguments are separated by commas. Note there's no parentheses. So the arguments are separated by commas. Size exceeded is argument 1. 10 is argument 2. So here's a possible invocation of it. I want to define a thing called bad arg, which is going to be an error message. It's going to say error, expected exactly 2 arguments. It's going to have a new line, and then I want to have error no be 1. So unfortunately to the NASM preprocessor, this looks like me trying to invoke error with 3 arguments. And that's just not done, right? I said 2 up here. Now I'm trying 3. It's not going to let me do that. It's going to complain. How do I tell it that really these 2 things, these first 2 things, are the first argument? Well, I enclose it in curly braces. So there we go. Or curly brackets. And there we go. So the curly brackets indicate this should be treated as a single argument. And so that's my first argument, and this is my second. This won't work either. The NASM preprocessor is very line-oriented. And so this was one line, and it was like, okay, a symbol. That makes sense. Fine. I understand that. Here's another line. Oh, here's a macro invocation, which refers to the symbol in front of it. There's nothing in front of it. I will issue an error and complain. Fine. You have to put the thing on the same line. There we go. Once you do that, it can then instantiate the macro. And what does that look like? Well, here is the body of the macro. And we're going to try to connect it to stuff up here in the invocation. The first thing to realize is that 00 gets replaced with bad arg. Great. 1 gets replaced with the thing here inside the curly brackets right here. And there you have it. And then 2 gets replaced with that. And so the whole thing looks like bad arg colon data bytes. There's a string and a new line, followed by .len equals $ minus bad arg. So now I define bad arg.len to be the length of this string. And then .erno. So now I have bad arg.erno equal to 1. And this tells me which error message I should set RAX or RDI to before I terminate the program. Great. If you want to actually see that expansion and not just talk about it, well, you may have noticed up here at the top I had a make line for this. It doesn't try to link it because what would it link? There's no code in here. Well, I can still put this through the assembler. And so I'll do that. NASM-F, L64, macro.asm, but look right here, there's a -E. This -E says, go ahead and run the preprocessor and stop. And so what I see then is the output from the preprocessor. So the preprocessor writes this out. It has this little directive, so it sets the correct line number in error messages, and one down here as well. But in here I see the full expanded macro right here, and it looks just like what we had up here, so we did a good job. All right, so that's pretty much most of what you need to know about macros in NASM. Lots of different ways to use them. They can be really helpful for big programs. If you ever have to write a big program, that'll be great. If you're just reading assembly from someone else, not going to help you much. But if you ever have to write some assembly, they can certainly help you quite a bit. And there are packages of macros out there. People have coded up macros for all the system calls, and they've coded up macros for certain APIs. And you can go and find those online, and they can be pretty helpful. Static single assignment. We've been looking at 2 types of analysis. We looked at control flow analysis, where I ask, where is the program control going? Which instructions execute, and in what order? And now we're looking at data flow analysis, where we ask, what values are in registers or variables or data structures in the program, and how do I interpret them? Clearly, neither one of those is going to be sufficient to analyze a program. I need both of them together. They're complementary. Right? I might know where control flow is going, but I don't know what the values are in variables, and pretty soon it will break down because I might do something like look up an address in a jump table, in which case, oh, crud, how do I figure out where that's going? Well, I need data flow analysis to figure out what variable is there so I know where the control flow goes. Or I might be looking at how a variable changes over time, and wind up in a mess because I need control flow analysis to tell me that I'm in a loop. So the 2 of them together are needed to analyze a program. Static single assignment, or SSA, is a very common technique for basic data flow analysis. So if I have something like what's over on the right, and I look at that, and I say, well, let's see, y gets x plus a. What's a? Well, a is x. Okay, y gets 2a, or 2x. Y gets 2x. There's my reasonable assumed statement of what y is. Seems reasonable to me. Well, a challenge to being able to figure out what that does is that I need to think about how values change over time. And that can make it somewhat hard. I can't just do your typical normal math stuff because x and y and a at different points could be different values. And things would be much better if x was always a particular value and y was always a particular value. And I can actually get there. That's called static single assignment, where a value is assigned to a variable exactly once and it never changes. And so how do I get that into such a form? Well, I do it just like we saw done earlier. We've actually done this once before in order to figure out the arguments to that big, complicated 7 or 8 argument function. And the way you do it is, in this case, I'm using subscripts. You can use anything you want to use for this, but subscripts seem to work pretty well here. So A0, A0, Y0, Z0, X0 are the initial values right before anything runs. What does this line do? It takes whatever the initial value of Y was and what the initial value of Z was, adds them together, and stores the result in X. So X is now changed, so I increment from X0 to X1. And so come down here, I set A equal to X. Well, that would be X1. And now A is changed, so it's A1. Down here, I set Y equal to X plus A. Well, that must be X1 and A1, which I'm storing in Y1. Okay, good. And now, because I have this single static assignment, Y1 is always the same value. It doesn't change. X1 is always the same value. It doesn't change. Y0 is the same value. It doesn't change. Y0 might be the same as Y1. It might be different. Doesn't matter. They don't change. And I can do usual math stuff, right? Y1 represents a fixed value. So I could say Y1, what is that? I just look over there and see that it's X1 plus A1 and just write that down. What's X1? Well, it's Y0 plus Z0. What's A1? It's X1. And so I just do back substitution. And Y0, Z0, X1 is Y0 plus Z0. Look at that. Y1 is twice Y0 plus twice Z0. I could have figured that out by looking at this. But my initial guess that this was 2x, that was wrong. It was sort of right. It was in that, it was x after being modified here. But if I'd gone and said, well, it's twice whatever the argument x to this program is, I would have been wrong, right? In fact, it doesn't depend upon x in any way, right? Whatever the initial value of x was, it's been erased here. And that makes sense, right? We said that that a variable is live if its value can influence the future execution. X's value is erased here, so x is no longer live prior to this instruction, right? Whatever its value was prior to this has been overwritten. It's live after this instruction because we use it right here and right here, but it's dead right before it. All right. So for straight code, it's pretty easy. This is the example we saw previously where we were figuring out the arguments to the function. And we just generated some static single assignment stuff over here. And we even did back substitution. It turned out RCX1 was the sum of all the 64-bit ints, including the one on the stack that were passed into the program. And it was pretty easy to figure that out because static single assignment is, for the most part, fairly straightforward and easy. Well, what if we make it more complicated? What if there's memory involved? Well, there was stack involved in the last one, but it was static. But what if there's memory involved that might change? So over here you can see we have memory references going on. And Well, in that case, we might just introduce the variable m to keep track of memory and subscript it like we do other things. And we can treat it as an array, and it can make sense to do that. Or we can give particular locations, symbolic names, or any number of other things that make sense to the program that we're analyzing. I've written some whole program analysis tools, and I've been on teams that have built whole program analysis tools, and we just used M to represent memory, and it rapidly becomes a mess. If you have other information, you really need to take advantage of it. We're going to look at things like Steensgaard algorithm and Mycroft's algorithm that will help with this, and maybe we'll get a chance to look at some shape analysis. And these are all different ways of dealing with the fact that there's this blob of bytes called memory. Its interpretation can change over time and can be complicated by pointers and other things. But for some simple analysis here, let's just say M is memory. We'll subscript it like other stuff and go on. What if there's branching? Well, there's branching here, right? So I come in here, I do some stuff, and then I jump if equal down to 20. Is there anything problematic about branching? Well, there could be. Right here, I might take a branch and go up here, right? There's a loop, I think, in here. It looks like a loop at least. And so suppose I have RDI 4 right here. And then I jump up here. Well, then I would need RDI 5, and I jump back, I need RDI 6. No, that won't work. I have a problem here in that I would end up with something that looks like recursion. So how am I going to deal with that? Actually, before we pick on that, let's pick on this aside down here. The code you see here is produced by compiling some very straightforward C code and then disassembling it. And there's a few things worth pointing out. Let's walk through the code real quickly, just because it's fun to, I think, get you into this mindset of how you analyze a program. So the first thing we do is we zero out EAX, right? We XOR it with itself. We see that and we go immediately, EAX is 0. EAX is the size of an int on our platform. So this says to me, hey, I bet there's a local variable called something. In this case, we're storing it in EAX, which is an int, and we're setting it to 0. So this is like int I gets 0. So I see that, and that's what I think. The next thing I see is this test of RDI with itself. So I'm checking to see if the 64-bit value RDI is 0. What's RDI? Well, 64 bits is big enough to hold a pointer on my system. So it could be anything. It could be a pointer. It could be a 64-bit int. It could be a weird way to pass me some floating point numbers. It could be pretty much anything, right? But I can reasonably say it's probably a 64-bit int, or it could be a pointer. So if this turns out to be 0, I will take this jump if equal, which is the same as jump 0, and I will go down here to 20. So I'll go all the way down here, and boom, I return. What's my return value? It's 0, because EAX is my return, and I set it to 0 up here. So if this thing was 0, I return 0. Okay, seems reasonable. So I keep going. I have a NOP. What the heck? These things just clutter everything up. Here's a no-op that just eats up some bytes. And it takes me from B all the way down here to 10, which is a nice aligned address. So the NOP is put in here as an address alignment, which leads me to conclude this is either the target of a call or of a branch or something like that. And I already know that it's the target of a branch down here, so I can see why it's aligned. All right, so they've aligned it because it's the target of a branch. It makes it a little faster. Again, you don't have to align it. It's just a way of getting a little more performance out of a loop. So align the top of the loop. What do I do here? Well, I go and look at what's pointed to by RDI, right? D word pointer. And I take the D word, right? That's an int. and I add it into EAX. I'm pretty sure RDI is a pointer, right? It's being used as a pointer. So this was checking for null. So it looks like the program was int I gets 0. If RDI is null, or whatever the address passed in, right? RDI is the first argument to the program. If that's null, I return 0. If it's not null, I come in here and I get the int that RDI points to, and I add it to EAX. Okay, I'm seeing what's happening here. So I gets I plus pointer, what do you want to call this variable? Then I do a move. Okay, what am I moving? I'm moving something into RDI. I'm moving the Q word. Again, that's big enough to be a pointer, or it could just be a 64-bit int, right? I'm taking RDI, I'm adding 8 to it. I'm finding out the value at that address, and I'm putting it in RDI. Well, I mean, I know what's going on here, but you can think about why that might be a reasonable thing to do and what that actually is, what the effect of that is. I will say that this 8 here, that's because there's a data structure underneath here that's not packed. And so normally it would like the assembler likes to align things on nice clean 8-byte boundaries, or in some cases 16-byte boundaries, and you can actually specify that when you compile. And of course then you can pack your structures as well so that they don't do that. In this case, the structure is not packed, and so it looks like there could be, right, a double word here. Maybe there's another double word we're not seeing that would fit in the gap, and then there's something here which is probably going to be a pointer because it's being put in RDI. I do another test to see if RDI is 0. If it's not 0, I go back up to 10. So this feels like looking for a null that terminates something and summing up stuff in EAX. And then if I don't do that, I hit this return, and I return the value that's in EAX. Why are there 2 returns? There's an op here. Why have 2 returns? Why not just have 1 return, right? Either have this jump go here, that'd be fine, or pick a longer NOP and have, right after this, have a bigger NOP and then have return. Why have 2 returns? Well, if I had a big NOP here, I'd waste some time executing that NOP. So I don't want to execute the NOP. I do it here because I'm right before a loop and it doesn't matter that much. I want this address to be aligned, right? Because it's the target of a jump. Sure, it's not a jump taken very often, but the compiler doesn't know that. And so it aligns that jump target for me. It wants this one to be right after this, so it's faster. It's just trying to make my code run faster. The fact there are 2 returns here should not scare you. It's still a proper program. These returns go back to the same place. They go back to the item that's at the top of the stack. Single exit. Single entry here, single exit, going back to where it was called, and then no unreachable or trap code. This is a little proper program. All right. So let's get rid of that stuff. Let's clean it up, right? Because we're not going to execute it. We don't care about speed. We want to analyze it. And that stuff's getting in the way of understanding what's happening. So we'll throw away the NOPs. They're gone. And we'll combine the 2 returns, and we'll fix this so it points to this return. There we go. Shorter, simpler code to analyze. Okay. We want to turn this into static single assignment code, but it's got branching in it. What does that look like? Well, let's build the flow graph for it. So I'll just use the address to label the nodes, and I wind up with this. Here's the flow graph for this little program, and it turns out to look pretty simple. I do 4, then do 6, check to see what's happening at 9. If it's true, out. If it's false, we go into here, and this is a little loop. We do 10, 12, and 16. We check 19. If it's true, we go around again. So this is a do while. Inside an if then else with an empty then part, and the whole thing is inside a sequence. So look at that. It's not just a proper program. It's actually a pretty nicely structured program consisting of sequence, do while, and if then else. This is a lot, and that looks short, and this looks long. How about if I just combine these little sequence nodes? Oh, that's a little bit nicer. So we'll combine the adjacent ones so that instead of having to write this whole sequence down, I can just write down, here's the sequence at this location. And that makes it a shorter, much easier to manage flow graph. Flashing red arrows is never a good thing. I have flashing red arrows, that's bad. What's happening right here? Well, these locations are places where flow merges. I go around here, come back, boom, I'm here. I come in this way, and I'm here. These are places where flow is merging from two different directions. And those are places that can be problematic for my static single assignment analysis. Why is that again? Here I might say something like RAX7 gets RAX6 plus 1, and then I go around and oops, now I've got RAX7 coming in, and so I need RAX8 gets RAX7 plus 1. Or I have RAX0 maybe flowing in here, and so this could be RAX6 or 7 or 0. I don't know, right? I can have different values of it depending upon how I arrive here. How am I going to deal with that? Well, I'm going to invent something to make the problem go away. And the thing that people have invented to make the problem go away is something called a phony function, which got classed up to be called phi functions. They were originally called phony functions, but then they had to write an academic paper about it, and you don't want to say your functions are phony. You want to make them sound important, and so you give them a Greek letter. They're phi functions, very important functions, phi functions. And I'll invent a phi function for each one of these. What will the phi function do? Well, the phi function will do magic. The phi function will tell me, oh, I know the value of RAX when it arrives here. I know which one of them it is. And just plug me in, and I'll take care of that for you. Really? Yep, really. That's exactly how it's going to work. And so here's what phi functions look like. Here's the first join point right here. This is sort of at 10, right? Because 10 is the first thing here. And you see up at 10, I have EAX gets phi of EAX from 9. What is that? That's the value of EAX that arrives on the line from 9. Or EAX from 19. What's that? That's the value of EAX that arrives on this line from node 19. So I'm coming from 19 or I'm coming from 9. And I may have different values of EAX. The phi function just picks the right one. How does it do it? Magic. Right? We don't tell you the implementation of it. It's just here as a placeholder. It's just a tool to get through the analysis. We need to do the same thing for RDI, which is another live variable at this point. So we have a phi function for it. You basically need one phi function for each live variable, mostly. If you really wanted to minimize the number of phi functions you need and to get a deep understanding of it, you need to read about dominance frontiers. We are not going to read about or think about dominance frontiers. We're just going to say, I need phi functions. And if I have too many, tough, I have too many. But I at least need one for each live variable, and so we'll go that way. Hope that makes sense. If you go to the web page, let's see, maybe Wikipedia maybe for static single assignment, it will probably tell you all about dominance functions and dominators and how they work in this graph. You don't care for this class. We're not going to make you learn all that. There's plenty of other hard stuff for you to learn. That's not part of it. All right. I can do the same thing for the second merge point. Now, my claim is I just have one live variable here, and it's EAX, because that's the return value. Is that true? Maybe. If I'm following the calling convention, it should be true, right? My caller should not look at the value of RDI when this function returns, because that's not part of the calling convention. But nothing prevents the caller from looking at that value. And that could be helpful, right? Maybe I'm calling something that did some crypto stuff and it left a pointer to a key lying around in a register, since that wasn't the return value, no one worried about it, and now I can go look at it and I can go find the key in memory. and maybe it's not been erased. Or maybe there's parts of the key material left over in the register, right? Register can hold 64 bits. That's a good-sized chunk of, let's say, a 128-bit key. That's half the key material. If I can find that, then I can cheat and use that to get me much closer to figuring out the key. Tricks like this. But we'll assume everybody's playing by the rules, and the EAX is the only thing that goes back, so it's the only live variable at this point, and so I just need one fee function, one for EAX. How do I get to the merge point? Well, I either come here from 19 through here, or I come here from 9 through this loop that, or this branch that bypasses the loop. So I come from 19 to 9, and so sure enough, I have EX from 19 or EX from 9. I'm going to refer to these argument spots here as slots of the fee function. So this fee function has 2. If the merge point had 20 things coming into it, I could have 20 slots. Okay. So let's go ahead and build a little table. And over here in this far column, I have the address. Here I have the instruction at that address, and I've included the fee functions in here. And here I have my SSA line. And so we'll use the addresses as subscripts. Why? Just convenient. So at address 4, EAX4, EX sub 4 is getting set to 0. All right? EX0 would be the initial one. EX4 is valued EX at offset 4. I said equal to 0 here. I could have said EAX4 gets EAX0 exclusive ORed with EAX0. That's true, right? But there's no reason for me to not say what I know, which is that it's 0. And so I'll just say that right here. We can proceed on. The next line, we do a test of RDI with itself. Do we change anything here? Well, no. Nothing gets changed in RDI or EDI, but wait. The 0 flag. The 0 flag at position 6 is going to be set if RDI 0, the initial RDI, is 0. So I might write it this way. And normally you don't have to keep track of flags. It might be relevant, and so you might keep track of it. It's really up to you. It depends on what you consider to be live variables that you need for your analysis, right? You're going to do the analysis based on needing to know something. And if you discover that you need to know ZF, you got to keep track of it, right? If you need it, then you need it. If you don't need it, then you don't need it. So we'll put it in here just to show you how to keep track of it. Now I'm going to do a jump if equal. Well, that's going to set RDI. Do I put RDI over here? No, I'm not going to put RDI over here. I've said RDI. RIP. It's going to set RIP. Do I keep track of RIP? I could. Right? I can have RIP at 9 but no, I'm not going to do that. So if the 0 flag is set, I'm going to jump to 1B. And if it's not set, I'm going to go here. So, but that's control flow information, and we're just doing a data flow technique, so let's forget about that. Does this change anything? Nothing we care about. So, blank line. Now we come here to 10, and we have the first of our fee functions. EAX from 9, so we look up here, there's 9, doesn't mention EAX. Look here, it doesn't mention EAX. Here it is, EAX4. So the value that's going to come to us from 9 is EAX4, so I'll fill that in the first slot of my fee function. EAX from 19, that's down here, and I haven't figured it out yet, so I'm going to leave that with a question mark. I don't know what that is yet. I do the same thing for RDI. RDI was not changed here, so its value is still the initial value. And then it's alternately it's whatever comes back from 19, and I don't know what that is. Now I do an add. So I'm going to go ahead and add into EAX the contents of memory at RDI. Now notice I gave these subscripts. So RDI 10, or RDI at location 10, is going to either be RDI 0 or RDI coming back from 19. And I don't know what that is yet. So there we go. Memory 0, because I haven't changed memory globally. I've just done that. And there we go, EX11 should be pretty straightforward, just adding into EAX. And you'll notice for my live variable analysis, if I decide to do that later, EAX is an L value, so its previous value is dead, but it's also an R value, so it gets to live again. So we kill the previous value and put a new one in there, and so if it was live before because we're about to use it, and it's live, it could potentially be live after because we've set a value that we can use. For our syntactic liveness analysis, it's live because it was an L value here. Move is the next thing. We're going to modify RDI with what's at memory. So again, we look at our memory. We haven't changed it, so it's still M0. We have RDI 10 because that's the most recent RDI. We add 8 to it. We go and dereference memory there, and that becomes RDI 12. We check to see if it's 0. Zero flag at 16 is true if RDI at 12 is 0. And then we do a jump. And the jump, of course, doesn't set or modify anything, so it's blank. Finally, we figured out what we passed 19, so let's go back up here and fill these slots in. So RDI coming from 19 would be RDI 12. So let's put it in here. There it is. EAX coming from 19 would be EX 11, and so we plug it in right there, and those are filled in. Down here we have another phi function to deal with. EAX coming to us from 19, that is EX 11. Or EX coming to us from 9, which is up here, and that was EX 4. Plug it in here. We know it's 0, so we could plug in 0, but let's just plug in EX 4 right now. And so at this point in the program, at 1B, we either have the value of EX that was in EX11, or we have the value that was in EX4. We then return, and we're done. So here's our static single assignment analysis for this program. It includes some stuff we could probably get rid of. We never modified M, so we could throw this away and just say M without a subscript. We never made much use of the 0 flag. We didn't really need it, so we could throw it away. And we'd have a little bit simpler analysis. So that wasn't too bad. It required that we create a phi function at each of the join points for each of the live variables, and then we filled in the slots based on what arrived. There was some tediousness. I didn't know what to put in this second slot here from 19. I didn't know what to put in one from here, so can I do a little better? Sure. Suppose that I kept track of the value of EX and RDI at every slot along here. Every one I specified it. Then I would have it specified at 19, and I could just go ahead and say it's EX19, and I wouldn't need to worry about that. That's what you do with symbolic trace tables. So trace tables, there's a bunch of different meanings of trace table out in the world. For the symbolic trace tables we're talking about here, they're pretty handy for just organizing your analysis. Now, we were able to do this. We used a little bit of intuition in doing this. If I'm writing code to do this, I need to avoid the use of intuition. I just need to have a procedure that you follow. And trace tables will give me that procedure. So we had to figure out the correct subscripts, and we lost conditions for some of the slots. We might want to keep condition information around, right? Conditions meaning we're going to take this branch if the 0 flag is clear, and this branch if the 0 flag is set, and I can know some of that information along the way, and I might want to keep track of it. Okay. And it's also not entirely clear that this helped us figure out what the program's doing. So let's go back to the analysis. If I try back substitution, what's going to happen to me? It worked just fine in other cases, and it would work fine for the body of the loop. But when I put it in this larger context and I say, what's EX at the end? Well, it's either this or this. Well, this is easy, right? I know this is 0. But what's this? What's 11? So I substitute EX11, and I substitute in EX10 plus the memory contents from RDI10. What's EX10? Well, I say it's either 4 or 11. Oops, I immediately have recursion, right? Because there we go. And so it can be tough to figure this out. And I don't have a lot of other context information. Like, I don't know what conditions lead to me choosing between these. All right, so that's what we're going to take a look at here. And we're not going to get the full answer to the program here because really you need both techniques. You need symbolic analysis, you need control flow analysis, and you need data flow analysis. Or you can just run the program. So there's many different ways to attack it, and you should feel free to use all of these. So for the trace table, we're going to create a table that has one column for each variable that we're keeping track of and one row for each program line. We're going to have a column for any conditions we know to be true at a particular point in the program if we think they might be relevant. And if multiple things happen on a given line, we'll just break it up into multiple lines. And so before we try to apply it to assembly, let's apply it to this program right here. You may recognize this program. We did our initial live variable analysis on this program, and we discovered that we didn't need both A and B. We could merge those two together and just use one. And so that was what we learned from live variable analysis. Can we learn anything by applying static single assignment to it? Well, let's see. We're going to build a trace table, and we're going to do the same kind of stuff we did before. So I'm going to go ahead and break out this piece. And in particular, I'm going to, because this is just initializing variables, that's just a return. This is really the core of the function. And really, even inside that, this is what I'm going to look at. I'm going to look at the body of the loop. So we're going to work from the inside out, starting here first. And you see, I hopefully have lined this up well. So for each line of the program, I have a line over here in my table. I have one at the top of the loop. This is the initial A, B, and C value when you enter the top of the loop. And then we'll work through here. I can invent phi functions and do other stuff for it, but I'm just going to look at the body of the loop right now. Hope that's clear. What does this first line do? Well, it takes whatever was in A, which right now is A0, and it adds 1 to it, and it puts that in B. And so I put that right here. B1 is A0 plus 1. But in addition, I also keep track of A, which does not change. A1 is A0. And I keep track of C, which does not change. C1 is C0. So every row, I have the value for all the variables at that position. For the next one, C gets C plus B. So A and B are going to stay the same, but C is going to change. And there we go. C2 is C1 plus B1. What's C1? It's C0. What's B1? It's A0 plus 1. So I could do back substitution to figure those out. And then I do the same thing for the last line. And so you see that's over here. I've modified A. B and C remain the same. And then I would potentially go around the loop again. But here is the net effect of the body of the loop. If I go ahead and take those final results here for A, B, and C, here they are over here and just shown vertically, I can do back substitution. And so B2 is just B1. There you go. C2 is C1 plus B1. So I do those substitutions. I repeat, B1 is A0 plus 1, and B1 is A0 plus 1, and B1 is A0 plus 1, C1 is C0. So I end up with this. Now, does that tell me anything useful? Well, it turns out it actually does. I do know something at the start of the loop. I know A0 is 0 because I initialize it up here. If I go on the loop again, then A0 is something different each time through. But let's just start with this and look at what the first iteration of the loop does. We just plug it in over here. So I plug 0 in, 0, and 0, and I wind up with this. A3 is 2. Really? Yeah, because this is 0. 0 plus 1 is 1. 1 times 2 is 2. 2. 0 plus 1 is 1. And this is just C plus 1. So here's what happens the first time I go through the body of the loop, right? So do while, so I'm always going to execute the body at least once. And this is what I get. Well, wait a minute. I only run the loop while a is greater than 9, and a is 2. So the loop body only runs once, and then the loop terminates. And I return C, which is C plus 1. So this whole program adds 1 to C. It takes its argument, C, and it returns C plus 1. That's what this does. That's what this does. It's a fancy increment. Would anyone ever write code like this? Yes. People who are malware authors would write code like this just to mess with you. And there's probably nothing in here that indicates to you that that's what it does, right? At no point do I write C gets C plus 1, right? I just don't do that, right? I write C gets C plus B. B is A plus 1. A happens to be 0, so really B is 1, and this is C gets C plus 1. Programming is hard. So now that we've seen how to apply a very simple form of trace table, we didn't keep track of conditions and all that other stuff. We just sort of put it in a broad context. Let's see how we might do it for assembly, and let's go back to our old assembly program. And I've written it over here, and I've broken things up a bit, and you'll see why as we get into it. Here's my phi function. There's EAX from 9, and down here I have EAX from 19. I've broken it into 2 lines. That's because I'm going to specify, if I know them, the conditions associated with each of those slots over here. I might know something, and it might be different, potentially. And since I'm trying to automate this whole process, I don't want to make too many assumptions, and so I'll just have 2 slots. Same thing for this one. Same thing for this one down here at the bottom. Phi functions occur at the join points, and there you go. The first part of this is easy. XOR EX with itself. I'm just going to go ahead and say that's 0. RDI doesn't change, and the 0 flag is set to 1. I'm going to keep track of it, and really, if I'm keeping track of this, shouldn't I have a phi function for ZF over? Yeah, I absolutely should, but I don't. Why don't I? It has to fit on the slide. Okay, you got to figure out what you want to deal with, and I don't want to deal with that. So I have lots of these cases where nothing changes. And notice my subscripts are all the addresses. So if I say, what's RDI at location 9? That's RDI, same thing as RDI at location 6, which is the same thing as RDI at location 4, which is the same thing as RDI at location 0. Nothing magical about that. Back substitution still works. I'll just have a value for every slot now. Let's put the phi function up. And so now I'm able to do precisely what I said before. I'm able to give you a condition for each one. So here, EAX gets EAX from 9, and I know what that is. That's EAX 9. Nothing complicated about that. But I also have to deal with EAX from 19. Well, that's EAX 19. Even though I haven't gotten there yet, I know that's what it's going to be because I have a value for every row. Right? It's not magic. It's just the way I wrote the table. And so I go right across here with this stuff, and I know some things. Curiously enough, I know that the 0 flag is 0 at this position. How do I know that? Well, I jumped if it was 1, so it's 0 here, right? The 0 flag is 0 here because I didn't jump. And I know the condition associated with coming in here, right? I know that 0 and 0, so I know the 0 flag can't be 1 because the 2 paths that bring me here both have the assumption that the 0 flag is clear. Is that true? Well, yeah, if I came here from 9, then I came here because the 0 flag wasn't set. If I came here from 19, well, I came here because the 0 flag wasn't set. And so from this information, I can conclude this. All right. So I got this stuff in the 0 flag column by looking over here at the conditions. So again, the conditions can be useful stuff. Same thing for RDI. right? Same conditions applied here, so the same result applies for the 0 flag, and I just plug in the right stuff here, right? Either I get RDI from 9 or I get RDI from 19. I can just go through the rest of it and I'm in pretty good shape. When I add, if the result of adding is 0, then I must set the 0 flag. I don't think I've written that correctly, but that's okay. It's not going to matter that much. I think this should be 10.3, and really, to be in terms of previous ones, this should actually be this expression right here. So this is an error on the slide. The 0 flag should be equal to, paren, that expression equal 0, close paren. And there we go. Check right on through it. All right, so like here, the 0 flag is set if RDI is 0. That's how test works. And so there we go. RDI, previously RDI 12. Many cells contain no change assignments. If I were writing this as a piece of code, I would have to waste space storing these no change things. Right? I need like an expression type which had an equality, maybe subtype, and had to specify the left and right values, and that wastes a lot of space. So how about I make a rule that says if nothing changes, then I can just assume, if there's nothing in the cell, I can assume nothing changes. If I do that, great, much simpler, and a lot less stuff to store. And so if you want to know what EX19 is, I would look here, and because there's nothing here, I would say, oh, it must be EX16. EX16 must be EX12. EX12 must be EX10, and that's right here. So I would just wind my way back through. Same as I've been doing before, but now it's explicit, and and everything can just be directly substituted. Again, back substitution is a bad idea, right? Because if I try to plug in stuff down here, I pretty rapidly wind up, even with these conditions, right? I wind up in some ugly recursive expression. I'll notice that if I come here from 19, I got here because the 0 flag was set. So I know that to be true, and so I know that. And if I came here from 9, then I came here again because the 0 flag was set. So I know that's true, and so I know along that path the 0 flag is set. And so this is convenient. I certainly have a case where ZF1B was 1 and ZF1B here was 0. That would sound like a contradiction. That's just telling me that I don't know what the 0 flag is at position 1B. But I do know what it is depending on which path I arrive. Okay? I hope that makes sense too. So again, back substitution, bad idea. We need control flow information to make this work. Remember how we analyzed that little C program earlier? We used information about the loop, about the fact that there was a loop, to simplify our analysis. And I hope that illustrates why you need things like loops, right? If I just had arbitrary control flows, spaghetti code go-tos and stuff, it would be much harder for me to say, oh, there's a loop and it only runs once. I'd have to do a much deeper analysis to figure that out. But if I do the control flow analysis and get things in a structured form, I can leverage that to help me with my data flow analysis later on. And maybe my data flow analysis reveals something I didn't know during control flow analysis, and I can go back and revise that. Right? Everything is a process of correcting your prior mistakes. All right. The thing we saw here over in that second column, that is, except for the few functions, that is disassembly produced from a very short C program. And it's a pretty trivial one. It's one that you've probably written. It's very easy. But even this, I mean, this doesn't give me keen insight into what that program is doing. Right? It's just a way for me to organize some of my analysis for it. To really understand what's going on, I need more information still. I need stuff like memory shapes, which I don't have yet, right? And which we'll see later. I need shape analysis and pointer analysis. I don't have those tools yet, but I'll get there. That's it. quick, short class for today because there's too much other stuff for me to do. Next time we meet, we're going to talk about another technique called program slicing. Slicing is a way for me to reduce the number of things I have to think about. And the things we've seen so far, live variable analysis, static single assignment, trace tables, they're all going to be useful as we build to slicing. So I'll talk to you next time.